My name is Bill Marinelli, and I was the project lead for the Mini-RF project.
My name is Michael Wargo. I'm the Chief Lunar Scientist for Exploration Systems here at NASA headquarters.
My name is Jason Crusan. During the development phase of the Mini-RF program, I was the COTAR, which is the Contracting Officer's Technical Representative, and then during the operation phase of the mission, I was the program executive for the mission. What those roles mean that during the development phase, the technical representative is the one that manages all requirements, project execution, schedule control, cost control, and all the logistics and administrative work on the contracts. And then during the program executive, in a traditional role, is the oversight and insight manager for the NASA project. The Mini-RF program began when we found out some interesting technologies that had been developed in the aerospace community. So we developed a program that would advance those aerospace technologies from flight systems on aircraft vehicles to space-hardened hardware. So we developed a program that had initially two flight builds, one that would fly on the Chandrayaan-1 mission aboard the first Indian spacecraft to the moon. The second one was on LRO, NASA's mission to the moon. We were looking at advancing certain subsystems that would be used for multifunction RF systems in our future communication relays. So it's a bit of a misnomer. We were our radar instrument, but we were also a multifunction box that would operate as a comm mode. Our emphasis on this from the Space Operations Mission Directorate was mainly on the RF subsystems base for future communications mode, and we got the radar and the science from the radar as kind of a bonus from that system. We were particularly interested in two subsystems, a wideband transmitter and a digital receiver and quadriform wave generation system that were pretty advanced in the aircraft systems world. But we had to develop new systems as well, including a lightweight antenna and some other hardware that did not exist. The goals and objectives of the overall program had twofold. So on the Chandrayaan-1 mission, we did have a lot of science goals and science performance. We were a single-band radar system, an S-band, and we had scientific goals of exploring the polar regions and mapping the permanently shadowed craters during that mission. And what we were also looking for is a return signature from the radar that was indicative of water ice in those permanently shadowed regions. For the tech demo that was on LRO, we went from a single S-band system to an S and X-band, brought in the dual multifunction aspects, and also added the communication modes. So the goals of having a two-flight structure like that allowed us to advance technologies, reduce risks of the manufacturing processes. So as we evolved to the more capable system on LRO, we could reduce those systems risks and advance to get to our real goal, which was the actual RF comm system capability that we were trying to get.
What we were trying to do is take airborne systems and show that we could space qualify them, but you needed to have some good space experienced people to make that happen, and a lot of them were unwilling to take that on. So it was a little bit outside their comfort zone.
Since the Mini-RF instrument was added a little later than the other instruments and was relatively immature in its technologies, we wanted to ensure that those kinds of qualities of that instrument didn't affect the performance of the LRO mission, its schedule, its cost, and its ability to deliver on its level 1 requirements. Mini-RF was added to the LRO complement of instruments, not part of the original plan of the 6 instruments that had been selected competitively. With the addition of an additional instrument with planning already underway, we believe that was added an additional risk to Lunar Reconnaissance Orbiter, and that had to immediately be incorporated into their ongoing planning.
When we started out with the Mini-RF program, it was fundamentally by its nature, the way we were setting it up. We weren't going to follow standard NASA processes or for that matter, standard DoD processes either. So our actual program management structure that we set up had a third-party implementing organization. It was a government entity, the Navy in this case, that was actually managing the acquisition and buy of all the subsystems for us. So we had an initial risk and that followed us throughout the system, which was we had an arm's length kind of relationship with the Navy, where they were our primary executing agents. They were serving as prime, for lack of a better term, for the mission. And that induced a risk so that we didn't have the traditional cost and schedule controls that you have over a contractor performing these things, where you have basic drivers like you must have this performance goal on this date and those kind of fundamental things that we have over contract vehicles. So that program management risk was one overarching deal. On the technical side, we were inducing a lot of technologies that were, in some cases, had flown in very harsh environments on aircraft systems. Our transmitter had flown in previous fighter jets and such, and it actually sits right above where the jet engine is. So we had really high qualified environmental components that were flying on those flights. And then we had other technologies like the antenna that we used, which had never been built before, and it was only a design on paper. So we spanned the whole TRL gamut from TRL 0 up to what would some kids consider TRL 5, and took those technologies from that state to flight for both builds in 30 months respectively for Sandrayan and 33 months for LRO. So bringing TRL from a low TRL to flight in that short amount of time was pretty challenging from the technical perspective as well. So one of the fundamental problems that we had was we did have low TRL technologies, and then we had this, how do you take TRL 0 to 3? And we had very hard flight dates. Sandrayan with the Indians had a hard flight date, and LRO had a challenging date as well. So how do you take low TRL technologies and get there in 30 months? So that was a pretty big challenge for us. So we did change a lot of our standard processes. We didn't do some of our standard quality assurance, but we did screen an enormous amount of parts, because we did use a lot of commercial parts, and we upscreened those. So we did take challenging risks on the reliability side, but then we proved to ourselves through testing that those parts could actually survive the environment for our mission duration that we needed to have. And then at the same time, we took a challenging approach on the LRO side, where our only requirement to LRO is do no harm to the spacecraft. So how do you prove that you will do no harm when you have high power electronics that are sitting on the spacecraft as it's going to the moon? So we had to prove to ourselves and to the LRO team and how we would do that. One of the material weaknesses we did have in our program was we did not have a strong systems engineering team from the very beginning of the program. We implemented an integrated product team approach for each of our WBS elements. So we had a software lead, we had a thermal lead, a materials lead. So we used that common structure. So we had subsystem leads for each of the discipline areas. But what we lacked is actually a strong systems engineer to integrate that. We struggled along with finding the right systems engineer when the government was prime and the Navy didn't have the depth that we would have liked at that point in time. But then we actually we mitigated that through finding other federal lab facilities, in this case the Applied Physics Lab, that did step up and help us in the system engineering role to pull everything together.
We didn't have a strong system engineering team at the government level. So what we decided to do was to try to work with the contractors, help them become part of the system engineering team. Even though it was a government-owned architecture, we could use, because it was our idea, we could use their system engineers to help us. The issue just becomes that they're still belong to their company, so it would be kind of a process to get to them, and not always would they support what we needed. So we had to have a lot of oversight on our part, especially for like me, to make sure that it was going in the direction that we wanted it to go in and not the direction the companies wanted it to go in.
One of the things that was identified very early in the mini RF development process was systems engineering as an issue. And it remained that way through a fair amount of the development cycle. And that was something that we reported back to our senior managers and to the LRO project. And over the course of time, that clearly was recognized within the mini RF project itself. And they worked hard to get their systems engineering approach stable and ongoing. And that occurred in time for it to be successfully completed, tested, and then integrated onto the spacecraft.
One of our fundamental flaws that we saw at the very beginning of the mission was since we didn't follow NASA standard processes and procedures, we actually cut out quite a bit of the standard NASA oversight and insight that we normally have. We actually managed the oversight of the contracts and the entire performance with a two-person NASA team at the beginning, without an independent review team. That was a fundamental flaw that we've identified relatively early in the program, and actually then stood up two independent review teams, one for each payload. The one on the Chandrayaan mission used an engineering lead from the Applied Physics Lab to run that independent review team. And then what we felt on the LRO side, the most appropriate thing was to actually use the LRO independent review team so that we could actually force synergy and actions across both programs from the spacecraft side and from the payload side. And the LRO team was augmented by some radar experts that were in the field at different NASA centers and out in industry to help drive our radar performance while still maintaining our comm capability. But it was a critical element to mitigate the risk of having the right level of oversight on the team as they performed. As any program, we had the standard three pillars of program management. It had the technical, cost, and schedule. We were technically trying to achieve the most capable radar system that's ever been built, and the first truly multifunctional RF system that would operate as an RF system and as a comm system. It fundamentally is a software-defined radio that also is a software-defined radar system at the same time. So technical challenges were pretty tough for us. The schedule side of this was also challenging. We had defined dates that we had to meet. We were a tech demo on LRO, so we were given a specific date that we had to be there and deliver upon, or they would fly without us. And that was a big schedule driver for us. So those being technical and schedule didn't give all that much. So cost did give a little bit more than we would have liked on the mission. We saw cost growth, but it wasn't out of the ordinary from where you'd normally see cost growth in a mission of taking this low of TRLs all the way to flight. That was our main challenge. And then the arm's length relationship we have with the Navy, and then the Navy's then contracted down to the performers, the subsystem providers. That multi-step process was incredibly challenging on getting accurate cost and schedule data. There was no EVM kind of flow, even though some of the subsystem providers did do EVM. By the time we got the data back to us, it would maybe 120 days in arrears. And in a program that's trying to develop hardware in 30 months, to 33 months, that's not acceptable. So we actually mitigated that risk through, we as NASA came in and we took over, and that was one of my jobs, we took over schedule and cost control and left the Navy in charge of the technical control of the performance. So then we ended up with a three-legged kind of stool management team with a Navy technical program manager, a NASA schedule manager, and a NASA cost manager. And the three of us worked together in concert to manage the demands on all three of those. But we could advocate for each one of them depending on what our viewpoint was. And it was important that NASA was in the schedule and cost control seats, meaning because we were the ones paying for the majority of the bill. And then at the same time, we were the ones that defined those schedules on the NASA side and being able to meet those missions. And then at the same time left the technical folks to push as hard as they could to get the most technical advancement out of the system. We had a large tech pull because we knew we had some kind of minimum requirements that we wanted to meet. But we also balanced that with a hard tech push to get the most capable system we could too.
As we were going through the project, then NASA, as cost escalated, then NASA wanted to put more requirements on us. And as they put more requirements on it, the costs would go up again because we had to answer all their questions. So what we worked out with them was a more unobtrusive way of oversight and just assimilating them into the team instead of having to do more reporting. They just heard the reporting that was done to China Lake.
One of the ways in which we were trying to ensure that we would be able to mitigate any risk that would be identified was to ensure that we had the right situational awareness for the instrument as it was going through its development phases. As a result, we had folks who were routinely at the reviews for Mini-RF, myself included, such that if any issues were raised, we could ensure that Lunar Reconnaissance Orbiter, the project office, was well informed and that they could respond early and maintain nimbleness in their planning to be able to, first of all, recognize that there might be a potential risk and be able to respond to it.
One of the integrated risks that we took, or we actually had to manage while we were working with the LRO team, is the do no harm aspect of this. There's a couple fundamental things, one of them being EMI. So we did have an S-band transmitter on our system, and LRO has an S-band transmitter. I believe they're within 100 megahertz of each other. So actually quite a bit of testing was done to make sure we didn't interfere with each other, we weren't transmitting and would cut each other's signals out for the mission. And that was a critical piece of integrated testing with us and the LRO team.
The concern always is when you have a powerful emitter like a radar on a spacecraft, especially when it's only a secondary kind of payload, that it could damage other systems. What we did early and worked with LRO is we modeled all the systems on the spacecraft with GRASP, and what that does is tell you what the radiation patterns are going to look like. Then you take that with all the filtering and all the receivers that are in line, and you figure out what power levels they're going to see at each of the receivers to see if you ever interfere. So we had a strong understanding that we were not going to interfere with them. We corrected our models based on some actual measurements made with the antenna. So from our standpoint, there wasn't really a major concern, but you have to go through the testing to prove it to folks. If you do the rigor of doing all the analysis up front, it helps you with the confidence that once you do it, it's going to work out well. Our mitigation for our program, we recognize several problems. We recognize that with a small government team from the executing agent that we needed to expand our team to include more. As we were going through the process of doing some of our designs, we realized that our specifications were lacking and people were starting to already design the boxes, and what we really needed to do and what we firmed up was a system engineering team. We brought the contractors and other agencies in to support us and help us get a good specification and then get correct requirements out to the vendors as they were building their documents. What we also had was a small government oversight team, and we strengthened that by bringing a couple folks from APL to help be part of the management team. So we split up the management team to really pay attention to the problem areas. So as we identified problem areas, we would sit down and work with each of the contractors. And what we tried to do with each contractor was have a top 10 list. And so whenever the manager would go or the system engineers would go to those facilities, besides the little issues that were facing the problems of the day, they always had to go through the top 10 list as well, because what we found is when you had problems, people always went after the fire drills. So what we insisted upon was a top 10 list. Some of the issues, as we found the system engineering team was weak and we had to do all these things, costs started to escalate. And with that, NASA wanted a little bit more oversight and a little bit more reporting. And what I basically told them is as we do more reporting and you have more oversight, it becomes more problematic and it will become more costs. So what we sat down and worked with them is to integrate the program team at NASA headquarters and a few support contractors into our team. And that way they got status, got to be able to see things as they were happening. They had their IRTs for all our reviews. So their independent review teams actually assessed our hardware even as we went through all our design reviews. So it gave them all the insight, but it didn't perturb our process. It allowed things to go through the same process without adding more bureaucracy. Just everyone was aware of what was going on. When you have risk areas within your hardware, if you can do parallel developments, sometimes it seems like it's more money to do that, but sometimes it's really just the upfront money. You'll end up paying it further down the road anyway. So what I've done in the past is you try to do parallel developments of difficult technologies or areas that you're really not that confident in. And also sometimes just to push some of the vendors. One of the things that we've seen and what we saw with the INT is the vendor became very inflexible to what the government needs were. So if you don't have any leverage, you're stuck. You're stuck with them all the way through the process because it's too late to do anything. So what we saw was the contractor was starting to provide all these in-depth policies for the INT. So the procedures became very cumbersome. Schedule was starting to slip. So what we did in the background was we set up APL to be able to step in case the contractor wouldn't do it. We gave the contractor contractual direction not to use all their policies, and that if they didn't, that we would remove the hardware from there. So in the meantime, while all the contractual stuff was done, we've actually set up a team and everything at APL because we really didn't have confidence that the contractor was going to follow our direction, and the contractor didn't. So once the contractor, they were given a deadline, said, at this time you need to show us why you're not going to use this policy. This is a Class D mission. It doesn't require these types of detailed quality requirements, especially on a procedural kind of basis. From a quality, yes. From a procedural, no. And so when we gave it to them, we said, basically by tomorrow at 9 o'clock, you need to show us that this is not going to happen and we will not be subjected to this, but how will we have a reasonable plan to go forward? They didn't think we were serious and didn't give us any response. So the next day we pulled the hardware and sent it to APL. It took us about a week to get the hardware packed up, shipped, and actually started testing at APL. So within a week we were back to operational, and our progress through APL was much quicker. So we actually, if you looked at the progression of things, we made a lot more progress in that month by making the move than what we had the previous month by leaving it at the contractor. We had 7 vendors providing each module that was going to plug into each other. So we needed to make sure from a project standpoint, from a radar perspective, that each vendor understood their interfaces clearly. And we did 2 things. One, we gave them all their own 28 volts power. Instead of figuring out to divide the power up, we gave them all 28 volts power so they wouldn't interfere in all the same requirements. And then from an interface standpoint to each other, we clearly defined them and worked with the project or LRO to give us simulators for the space-wire interfaces and all the interfaces that really talk to each other and that would eventually talk to the spacecraft. So as we developed each module, they had good emulators that were controlled. I mean, they were up-to-date, CM controlled, so what we actually saw was what the actual configuration was there, and that was the same thing for LRO. LRO provided us all the emulators for their system as well, and on top of that, they had a little flat set that they had developed with pieces of the brass board and breadboards that they had from each of the other systems. As we had developed our breadboards and brass boards, we would put them onto their flat sat as well, so we would actually see the real hardware, and any differences would then get reflected in the emulators and then also in our design. So once we actually put all the flight hardware together, it was a very, very smooth transition. During the design phase, instruments and the spacecraft are not always in the same place. So a lot of times, and what LRO did is they really went and tried to define worst case scenarios for us. So as we're building the hardware, we can understand what to build to. The problem is it's a lot easier to build to a requirement than it is to have them change that requirement on you in the future and make it worse. So sometimes you sit down and they give you worst case scenario type requirements. If you have issues with them, then you negotiate, well, how do we work these issues? But if you can meet the worst case design requirements, then you just keep going forward, and that makes it a lot easier. What I've seen on other spacecrafts, and even with the Indian spacecraft, was they gave us all the requirements and then changed some of them at the last second, which we couldn't do anything about at that particular point. So it really makes it problematic if you wait until the last second to do those things. If you define worst case scenarios and worst case requirements for folks and are willing to work through the details of the individual places that are problem areas instead of just trying to work the details of each one.
One of the challenges we had was we had very tight spacecraft to payload interfaces, both on the Chandrayaan side for the Indians mission and on LRO. And we pushed ourselves from a technical perspective way harder than we had to for the first time we ever built this payload. Initially we had, for our Chandrayaan mission, we had an entire payload requirement of less than 10 kilograms. That actually moved down to 8.5 kilograms for all electronics and antenna and all the support structure for that. At the end of the day, we had an interface issue with the Indians. It was a machining interface issue on the spacecraft side, and we ended up adding a 1.5 kilogram plate underneath our box. So we challenged ourselves significantly on reducing mass. At the end of the day, we actually got mass added to our payload because of a machining issue they had, and they actually had mass margin. If we would have gotten that mass margin at an earlier stage, it would have reduced our costs significantly, and we wouldn't have pushed ourselves to be as lightweight as we had gotten, and we could have made some of those trades earlier. And likewise on the LRO side, we actually carried a significant risk. We actually carried significant challenges in trying to get to the low mass for LRO as well. And at the end of the game, once we had our independent review team, they were actually able to mitigate and work between the LRO side and the Mini-RF side to get us an additional mass allocation, which if we would have had that earlier, that would have significantly saved us cost. But we had many discussions where we were arguing over hundreds of grams. And then at the end of the day, when you add a 1,000-gram plate underneath yourself, you kind of kick yourself a little bit for that when you should have asked for it in the first place. We actually went above and beyond in the screening of our hardware. We screened over 300 new parts. We took many things to the radiation beams to do radiation testing on them. But at the same time, we also took commercial risk with commercial parts. So we actually have parts that are commercial parts that, in theory, will not survive the radiation environment. But then we mitigated that risk through every single time we operate the instrument on orbit, we actually do a power on, power off cycle, and we actually reset ourselves every single pass that we take on orbit operationally. So we use our ConOps to also mitigate our technical risk of the hardware. So your most likely event in most of these cases is single event upsets. So our standard ConOps is that we just reset ourselves every single time we take a pass. So that mitigates that risk, and it's not a destructive failure, it's just a failure for a single pass. You only miss one pass of data, not the entire mission. One of our fundamental challenges that we're given by senior management is how do you acquire technical capabilities in a different way? And we were given pretty high, broad latitude to figure out what the right way was. So we were given the leeway to take 7120 and take out the pieces that we wanted and leave the pieces we did not want because we were a demo. One of the strong lessons learned, though, is fundamentally at the beginning we took out too much. We went down to a floor that was just unacceptable as far as level of insight and oversight, and let the technical folks go a little bit too long before we got a little bit of cost control and schedule control in place. But one of the key lessons learned is where do you dial that back to? So what is your new floor of minimum requirements? Instead of waving down to them, how do you create a floor from the very beginning? A floor that is acceptable, and it gives you the right level of independent review on the technical performance side, but also the right level of independent review from a cost and schedule perspective. So, yeah, on a tech demo perspective, you don't want to throw the entire 7120 at the program, but then you can't just remove it all either. So somewhere in there's a happy medium. I think we found that happy medium in our program, but we would have liked to find that at an earlier stage in it, and it probably would have saved us some schedule and actually gotten us higher technical performance. So the Mini-RF team consisted of about 8 main companies that were spread across the entire U.S., everywhere from Raytheon on the West Coast to Raytheon in Tucson, Arizona, to APL here in Laurel, Maryland, to BAE in Manassas, Virginia, to Northrop Grumman in Chicago. So we had this very disparate team geographically, which was challenging in itself. And each one of these subsystem providers had never worked together in most cases. In the essence of trying to build Mini-RF, we used a broad agency announcement type strategy with the government as prime to do our acquisitions. So we were able to pick best of breed of every single subsystem, but that also meant that there wasn't a working relationship with those folks. So systems engineering struggled because of the high complexity and the number of folks that we had working on it. At the end of the day, it did work, but it was a challenging area that took an absorbent amount of the program management team and project managers team to pull that together. And a stronger systems engineering team at the very onset of this would have mitigated that risk, and it was a strong lesson that we learned.
There's 2 lessons here because, one, a small Class D program from a company standpoint doesn't necessarily draw the attention that it needs at a company level. When they have, especially large companies, when they have billion-dollar programs, couple $1 million here or there really doesn't necessarily bring a commitment on their side. We saw a lot of our support go on and off from the contractors because they had more important programs that were much more expensive programs to the company. So we could see them get pulled off our contract real quickly. From the agreement on the MOA, it's more of, from the government standpoint, if we have an executing agent, to make sure that they have all the resources and committed the resources necessary too. And also, the problem with MOAs is a lot of people look at them as they're not worth the paper they're written on. And so people feel like they can get in and out of them fairly quickly. What the government needs to be able to do is, if people aren't following the MOA, they really need to reconsider continuing that MOA or finding another way around that. But MOAs at this point, people kind of take as a handshake, and that's about it.
As we went through the development of LRO, I think the key to managing the risks on a really practical level were, first of all, having and recognizing the need for situational awareness and early as possible understanding that the risk posture may have changed, and also to have a well-oiled communications path among all of the major elements within the spacecraft, and also with each of the instruments, and with Mini-RF specifically, because of the special circumstances that it was added to the mission. So a combination of early understanding, identification and understanding of the risk, having a systems engineering team that understands that to be able to mitigate that risk, flexibility and nimbleness is necessary, and then having the communications to ensure that everybody understands what the current plan is and what that means with respect to when they need to be able to either deliver an instrument or be able to demonstrate that a risk has been mitigated. I think one of the design features of LRO that allowed us to be able to handle the challenges and the issues that arose with Mini-RF was the original design approach for LRO. When you look at how the instruments are situated on the spacecraft, any of the instruments could be integrated pretty much at any time, that you didn't have to put one instrument in place before you put another one in place. Being able to have that kind of a spacecraft bus design gave additional flexibility to the test and integration schedule for the instruments, such that as small issues arose for each of the instruments, that the integration and test team had the flexibility of being able to accept another instrument a little bit earlier, potentially another instrument a little bit later, because they were still handling some of the problems. That approach to systems engineering and integration and test really was a terrific mitigation technique that worked very well in the case of LRO, and specifically with the case of Mini-RF. Based on the approach that LRO took for acquiring the instruments and being able to accommodate an additional instrument a little bit later in the game, I think a couple of things that we've learned from this is that at the beginning you see it as an issue, that this isn't something that we were originally asked to do, so it's an additional burden on us. But if you open up your thinking to how can we accommodate that, and how can we do that without an impact on our primary mission, later on you can identify that there is potentially additional value that accrues from having that instrument on board, and it can provide key information that will help us to plan for future exploration, in this case of the moon. Having that kind of flexibility and recognizing that there is a potential upside for every one of the issues that you have to deal with leads you to develop an overall mission planning structure that in effect can give you a much bigger payoff in the end by providing the resources and the commitment to accept the technology demonstration and to really do it right. We end up with an instrument that's providing additional information that we didn't originally expect. So one of the things is to when you're asked to accept an additional requirement, look at that requirement in the light of how potentially can it benefit us, rather than just saying, here's something that is just now going to knock my plans and schedule on its ear. That originally you've already built in the flexibility of in how you're designing the overall mission that will allow you to accommodate something like this. And in the end, you end up with additional benefit for exploration and for science.
Fundamentally, we now have this capability within this set of hardware for broadband and multifunction radar and communication systems. In the past, we've always thought about communication capabilities as entire satellites, as relay satellites, as our TDRS relay satellites. We have some experience with the Mars program where we've developed payload-level comm units. They have limited functionality and they're appropriate for those types of missions. But now what we have is this multifunction, highly capable box that could allow us TDRS-class communication systems as a payload on a mission instead of just dedicating an entire relay satellite to it. If we only work for technology pull from a program, then we're never going to push far enough to get those technologies that we really, really want. And we need to be able to balance between push and pull to be able to get us to advance our TRL basis in a lot faster way. Because we learn so much through flying these things early. By the time we get to the flight systems, then we have this knowledge base that we can build off and then, in essence, lower our risk in the long term. One of the things I'd like to take away is we want to share this knowledge with as many people as possible. So I want to encourage you to, if you want to talk to us, reach out to us so I can point you to any one of our members of our team. If you want to understand how we do thermal design, if you want to understand how we did our software design or our overall processes and lessons learned, I encourage you to contact me or anybody within the Space Operations Mission Director, and we can point you in the right direction.